Hello and welcome to this recording for SPSS and how to conduct a simple linear regression in SPSS. So what I have open here is the CHIP dataset, and CHIP has a variety of different variables, including height and weight. And so what I'd like to do as a demonstration is show that there is, in fact, a correlation between height and weight. In other words, the taller a person is, the more they're likely to weigh. Now, of course, there is a variety of weights for any given height. But first of all, let's go ahead and take a look at the scatter plot so we can just get a pretty basic visual. So our first step is to go to Graphs, Chart Builder, and we will click on the scatter dot, and this top left corner, we'll just drag that up here. And then over here on the left hand side we have all of our variables, and you'll notice here's height and here's weight. And the interesting thing is normally we think about height as being a continuous variable. So this is part of the reason that I wanted to show this analysis. I'm going to do it two ways. First, I'm going to leave it just like it is. So let's go ahead and put height here on the x-axis. In general, we put the independent variable or the predictor variable there. In other words, height is a good predictor of weight, how much a person weighs. So we'll put weight on the y-axis or the dependent variable, and then I'll just click OK. And the thing that you'll notice, here we have a beautiful graph, and it looks like it goes all the way from 54 inches all the way up to 76. Now, one of the problems that you see here is it jumps directly from 54 to 56, 57, 58. Remember how we noticed that height was coded in this particular data set as if it's ordinal, and as long as it's ordinal, it's just going to treat each one of those as categories. And so, of course, it's just going to jump from one to the next. So you see these neat columns, and that's just an artifact of the fact that we round pretty much everybody's height to the nearest inch. So we'll see that regardless of how we code that. But the thing that I'd like to do now is go ahead and go back to my data set, and instead of having height here be an ordinal variable, what I'd like for it to be is scale, because truly that is more of a scale variable. If I go to my data view and I look at height, like if I had done that before I just did that, 62, 65, 68, 64, 70, and so on. These seem like there's an equal distance between each of those variables. So remember, scale is that kind of variable that has units of measure, height in inches, weight in pounds. And so it qualifies as that, and we want to treat it that way so that we can get the most out of that variable. Let's go ahead and go back to graphs and make that chart again. I'm going to see how it still has height as an ordinal variable. I'm going to do reset, so it gets all of the variables out. I'll start over and put my scatter plot there. I'll put height here on the x-axis, weight on the y-axis, and click OK. And now when I look at my variable, you'll notice that this looks a little bit more like a ruler. In other words, that person who was 54 is 2 away from the person who is 56 in this particular view. And so it may change your view slightly if you go from something that's coded as ordinal to something that's coded as scale. So it's not neat little categories anymore, although you still do see this digit preference, what we call where we tend to round to a specific instead of recording it exactly. Okay, so there's a scatter plot. I'm going to show you one thing that you can do with this scatter plot, and if I double left click on it, it opens what's called the chart editor. So you'll notice that this graph is still there in my output viewer, but now I have a new window called the chart editor. Up here near the top, there's a little picture with a line going through the dots. I'm going to click on that, and here it gives me some options. I'm going to add a fit line that's linear. I don't need it to be a variety of other shapes. I'm just going to add a linear line and click close. And the thing that you'll notice now about this line is that it added an equation for that line, and it also added an r square. And so the thing about the chart editor is it kind of exists out here. As soon as I close it, then those changes happen to the graph that's in the output viewer, the SPSS output viewer. So here's my line. Y is equal to negative 1.94, and E2 just means exponent 2. In other words, times 10 to the 2. So this would be negative 194 plus 5.64 times x. So we're going to see that equation later. I want you to have noticed it. And here's our r square for that line is 0.277. So this graph that we made just gave us a whole bunch of information about our best fit line, about our regression. The next thing we're going to do in this video is we're going to run the actual regression analysis. So we'll go to Analyze Regression Linear. So Analyze Regression Linear takes you to a dialog box that allows you to ask a specific question. Here we are asking or testing the hypothesis, are height and weight related to each other? In other words, if I know something about height, remember how I said height is my independent variable or my x variable, then maybe I also know something about how much a person weighs, and that's my dependent variable. So that's really all I've done. I put height and weight into independent and dependent. So that's the basic part of regression. If I hit OK, I would still get quite a bit of output. I'm going to do two more things. I'm going to click on Statistics and ask for confidence intervals and descriptives. This descriptives is a shortcut because remember, as part of any analysis, you need descriptive statistics for the variables individually. So this is what will get you that. The confidence intervals give you confidence intervals around the beta coefficients, and so that's just a nice little added thing. I'm going to click on Continue. And then remember, one of the assumptions is normality of residuals. And so I'm going to make myself a histogram of those residuals by clicking on Plots, and then under Standardized Residual Plots, click on Histogram and Continue. So I added a couple of things under Statistics and Plots. I'm not going to add anything else. I'm going to click on OK, and then SPSS will create my output. So let me walk you through this output really quickly. Remember how I asked for descriptives? That's what got us this first box. So the average baseline weight is 175. The average height in inches is 65.42. And we have standard deviations, and the sample size is 426. I also get a correlation between them, which is 0.526. You'll see that number here a little bit later again, because remember, Pearson correlation is R. We can skip this box. Here's my Pearson correlation again, R, 0.526. And then remember on our scatter plot where it said r squared is equal to 0.277, here's that number again. Literally, if you got a computer out and you put 0.526 and square it, you would get 0.277. I have students ask about that all the time. Well, how do you get r squared? R is like a correlation thing. Well, you take r and you square it and you get r squared. So there we have it. And then this next box is what's kind of the meat, the most important part of the simple linear regression. This is where we get our sum of squares for the regression and the sum of squares of the residual. In other words, how much of this is due to the line and how much of it is noise. Kind of like that background, just variability between people. And we can see that a big part of it is due to the regression. When we divide the sum of squares by the degrees of freedom, we get our mean square. And when we take the mean square divided by of the regression divided by the mean square of the residual, that's what gives us F. In other words, 182,000 divided by 1,000, roughly. I'm rounding to describe it. But that gives us an F of 162, which is very significant. In fact, it's kind of like beyond where we're measuring to 3 digits of a p-value. And then this next one is the coefficients box. And this is actually the way we report simple linear and multiple linear regression in a standardized kind of paper, because what we're after is we're looking for this beta coefficient, 5.643. Now, do you remember how on the scatter plot that we drew the regression line, we had y, which is baseline weight, is equal to negative 194. Now they had an exponent in there, but it was negative 194 plus 5.64 times x. So this information right here, the baseline weight, the constant, the beta coefficient, and height, you can create your regression equation from those 4 things right here. We also have a t-value for height is equal to 12.752. I challenge you to square that and confirm in your own mind that t squared, in this case 12.752 for a simple linear regression, is equal to f, which is 162.607. Now, of course, these are rounded. If we knew the number farther out, they would be exactly equal. But to rounding error, that's what we get. And this p-value for the bottom row should always equal this p-value here for simple linear regression. And this 95% confidence interval for beta, anywhere between 4.77 and 6.51. We say our beta coefficient is 5.64, but we are 95% confident that it's somewhere in that range for the population. So that's our 95% confidence interval that we asked for extra under statistics. So here's our histogram, and these are the standardized residuals, and this needs to be normally distributed. And if you're just eyeballing it, you'll say, oh, there's kind of like a gap here and a little bit of a gap over here, looks like it's a little right skewed, and you're right. Based on my experience, I would say that this is pretty close. And especially with a sample size of 426, that this is good enough. Doesn't look obviously to have 2 humps, bivariate. It doesn't have anything, any really big issues going on there. So that is a summary of how to perform SPSS and interpret the results in SPSS. Thank you so much for joining me.